Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 4, Solving Exponential Equations Using Logarithms. In our last unit on exponential functions and exponential equations, we really saw very limited ways that we could solve exponential equations. And by an exponential equation, what I mean is an equation where the variable that we're solving for is in the exponent as opposed to the base, right? We had the method of common bases, and we also solved a significant number of those equations using graphical means and our graphing calculator. Today, we're going to see how we can use logarithms to solve many exponential equations. So let's get right into it. All right, here we go. A key fact. Logarithms are the inverses of exponential functions, right? They give us, as an output, right, the number that we have to raise the base to in order to get the input. Using that, they can help us solve equations that involve exponential functions as long as a key fact is understood. Let's take a look at that fact. For any base b such that b is greater than 0, the following is always true. The log base b of b to the x is equal to x. Now, let's talk about this just for a moment. All right, I really want you to internalize this. Okay, exponentials and logarithms both have a base, some constant number. All right. The logarithm of a particular base, let's say base 3, is the inverse of the exponential of the same base, 3 to the x. Now, logarithms, keep in mind, give us the power that we have to raise that base to in order to get the quantity inside here. So it should stand to reason that the log base b of b to the x is equal to x, because what do we need to raise b to in order to get b to the x? Well, we have to raise it to the x power. Now, what you really want to sort of be able to do is just think about it as the log base b of b to the x. The log base b and the sort of b here cancel, leaving you just with the x, just with the exponent. Now, let's do a very simple exercise to make sure you understand that idea. Exercise number 1. Simplify each of the following expressions using the fact above. Letter A, the log base 2 of 2 to the 8th. All right, well again, this thing is literally saying, what do we have to raise 2 to in order to get 2 to the 8th? Well, that is, not surprisingly, equal to 8. Now, the rest of these things involve variables, which is important because we're going to be solving exponential equations. But just really quick, right? You know, if we've got our calculator, and we do have our calculator, I'm using the TI Inspire, and we go to our general logarithm, which we looked at previously, and we looked at, what was this? This was the log base 2 of 2 raised to the 8th power, right? There's that 8. All right, and it wouldn't matter what power I put in here, right? If I went up and I grabbed the log base 2 of 2 to the 13th, it would give me an output of 13. Because of course, what do I have to raise 2 to get 2 to the 13th? 13. 2 to the 8th is 2 to the 8th, right? Simple as that. Now, that should then give us a very good sense for where we're going with the rest of these things, right? Let's take a look at letter B. Here we're dealing with the common log, remember? So in letter B, when I say the log of 10 to the x, that's really the log base 10 of 10 to the x. And in fact, this thing, let me just rewrite it as log base 10 of 10 to the x. Literally, we can kind of think of those canceling, and we've just got x, right? What do I have to raise 10 to in order to get 10 to the x? I've got to raise it to the x power. All right, why don't you go ahead and do C and D? Hopefully they're pretty easy for you. Go ahead and try those. All right, well, the log base 3 of 3 to the 4t, what do I have to raise 3 to get 3 to the 4t? Well, I have to raise it to the 4t. Now, the bases don't even have to be particularly nice. In letter D, I have log of base 0.5 of 0.5 to the t over 4. What do I have to raise 0.5 to get 0.5 to the t over 4? Well, I have to raise it to the t over 4. As a side note, if you're wondering why in letter C and letter D I've got the variable as t instead of x or y or something like that, you can probably anticipate that many of the exponential models that we're working with use time as their input, right? And we almost always represent a time variable, whether it's in hours, days, minutes, etc., with the letter t. All right, so now let's actually get into the weeds. Using logarithms to solve exponential equations. Since all modern graphing calculators can find a logarithm for any positive base, we can use this technology to solve equations involving exponential expressions. So let's take a look at a very, very simple one in exercise number 2. Consider the equation 4 to the x equals 10. Letter A, using a logarithm with an appropriate base, solve this equation for x. Round your answer to the nearest hundredth. Now, just as a side note, before we go on and do this, which is going to be very, very easy, all right? In our last unit, the only way we could have done this is either by finding a common base for both sides, which would be very, very difficult because 4 and 10 don't have any sort of naturally occurring common base, all right? Or we would have graphed y equals 4 to the x and y equals 10 and found their intersection point. That's fine, but it takes time, right? And it takes a lot of technology. So let's take a look at how we can do this with logarithms. Now obviously what I want is I want x equals. In order to do that, I kind of want to cancel that logarithm. To do that, what I'm going to do is I'm going to literally ask the question, right? What do I have to raise 4 to in order to get 10, right? I mean, that's the question I'm answering. What do I have to raise 4 to in order to get 10? And it's not a nice number, right? Because 4 to the first is 4. 4 to the second is 16, so it's got to be somewhere in between those. And in order to answer that question, I'm going to take the log base 4 of both sides. Log base 4 of 4 to the x, if you want to think about it, cancels each other out. Now, they don't really cancel each other out so much as just saying, hey, what do I have to raise 4 to get 4 to the x? Well, that's x. And now x is equal to the log base 4 of 10, and that's where we need our calculator, right? That we can't do in our head. That's okay, right? I just bring my calculator out. I go in to the general log function. I put log base 4 of 10. I hit enter. I see that it's some messy, irrational number, 1.6609, etc. This one asked me to round, I believe, to the nearest hundredth. I think, let me just make sure. Round your answer to the nearest hundredth, absolutely. So my answer is going to be x equals 1.66. Now I think I'm going to keep my screen like this just for a moment so that we can take a look at letter B. Check your answer from A in the original equation. Why does it not quite check? All right, so let's do this one together. It's easy enough to check x equals 1.66 and 4 to the x equals 10. So what I want to do is I want to look at what 4 to the 1.66 is equal to. Let's grab our calculator. We do 4 to the 1.66, and we get, 9.98. Apologize for that. 6 ... right? And I'm feeling pretty good, right? I was looking for the exponent I had to raise 4 to in order to get 10, and when I did 4 to the 1.66, I got 9.986, etc. Pretty darn close. And of course, why does it not quite check? And it's because we rounded the value of x. Simple, right? We rounded the value of x. And we could, do sort of a little experiment, and we could take x out to the nearest thousandth, and see what 4 to that is, and then x to the nearest 10,000th, etc., etc. And the farther we took x out, the closer 4 to that value would be to 10. All right? But ultimately, we have to round somewhere in this problem, and they told us to the nearest hundredth. All right, but it's that easy. All right, and notice how I said, use a logarithm with an appropriate base. And the appropriate base will always be the same base as the exponential. You want to get that inverse in there, right? Solving equations is all about using inverses, right? The inverse of addition is subtraction. The inverse of multiplication is division. And the inverse of exponentiation, like this, is taking a logarithm. All right, let's keep working with these. Solving more complex equations. Certainly exponential equations can be more complicated than the previous exercise, right? 4 to the x equals 10. The key will be to isolate the exponential expression and then use a logarithm of the same base to eliminate the exponential. All right, so let's take a look at exercise number 3. Solve each of the following equations. Round all answers to the nearest hundredth. Use logarithms with appropriate bases. Check your answers. All will be slightly off because of the rounding. All right, so this is simple enough. It's actually not that different than normal equation solving. Here we have 5 to the x minus 7 is equal to 20. We've talked extensively over the years in various courses about how to solve equations by thinking about reversing the order of operations. Of course, the order of operations is I do 5 to the x first, then I subtract 7. So in order to undo that, I'm going to undo it in the opposite order in which it was done, using inverse operations. So let's do this together. All right, I have 5 to the x minus 7 is equal to 20. Since I subtracted 7 as my last operation, the first thing I'm going to do is add 7. Now it might be very, very tempting to divide by 5 right now, but keep in mind we don't have 5 times x, we have 5 raised to the x. So my next step, when I extend my page a little bit, is going to be to take the log base 5 of each side, right? The log base 5 is the inverse of 5 to the x. Those now cancel each other out, giving me just x over here, and my exact solution is really log base 5 of 27. So let's just pause for a moment, right? If this was a multiple choice question, they may actually have this as the final choice, right? And this is the exact answer. The exact answer is log base 5 of 27. Now in this particular problem, they said round to the nearest hundredth, all right? And that's simple enough. Let's do this one more time on our calculators. We just need to figure out what the log base 5 of 27 is. There it is, right? 2.047, etc. Rounded to the nearest hundredth, 2.05. Let's go back in and let's extend the page a little bit more. X equals 2.05. And now let's go back up to the rest of them. All right, so let's do one more of these things together and then we'll have you do letter C on your own. Let's take a look at letter B. Here we have 2 raised to the t divided by 4 is equal to 11, all right? And we want to solve for t. Now, keep in mind, right, order of operations. What's happened here? T has been divided by 4, and then we've exponentiated, if you will, that quantity with a base of 2. So actually, the exponentiation is the last thing that was done. So the first thing that we're going to do to unwrap this equation and get our t out of it is to do the logarithm, right? We want to get the t divided by 4 all by itself. So, whoops, we're going to do the log base 2 of 2 to the t divided by 4 is equal to the log base 2 of 11. These are going to cancel. That's going to give me t divided by 4 is equal to the log base 2 of 11. Now, before we finish this off, let me just make a little comment here, right? A lot of students will very understandably want to right now figure out what the log base 2 of 11 is, and you can do that. And then, you finish off the problem. I like to wait to evaluate the logarithm as long as I can because I don't want to have to carry messy decimals with me throughout a lengthy problem. So before I ever do this, I'm just going to leave that the way it looks. Now, to get rid of that division by 4, I'm going to multiply by 4 on both sides, and I'll find that t is equal to 4 times the log base 2 of 11. And now what's easy is I can put that all into my calculator at once. So let's do our calculator again. Let's bring it out, right? Let me just kind of clear this thing out a little bit. So I'm going to just clear my history out. All I want is 4 times the log base 2 of 11. And that gives me 13.8377, etc., Rounded to the nearest hundredth, we've got 13.84. 13.84. Sometimes those decimals just don't want to draw on this board. All right. So let's have you work on letter C, which is a little bit messy. All right. I know that we've got an exponential with a base of 1.025, but you know what? Your calculator doesn't care. It'll take any positive base you give it, whether it's a whole number, like it was in A and B, or whether it's a decimal, which is what it's going to be like in letter C. Try to leave as much as you can for your final calculation so that nothing gets lost in intermediate rounding. Pause the video now and see if you can figure out what the value of x is in letter C. All right, we've got 250 times 1.025 to the x equals 900. Again, thinking of order of operations, right? We've got the exponentiation coming first, then the multiplication. So when we undo all of this, the first thing I'm going to do is I'm just going to simply divide by 250 on both sides. Let me rewrite the equation down so that you can see it a little bit better on your tiny screens. So I'm going to divide both sides by 250. Now again, just like before, it's probably tempting to figure out what 900 divided by 250 is. Actually, I'll write that now without the parentheses. We don't need that. But I'm just going to leave it like 900 divided by 250. There's really absolutely no motivation that I have for figuring out what 900 divided by 250 is. I'm just going to leave it like that. I'm now going to take the log base 1.025 of 1.025 raised to the x is equal to the log of log base 1.025 of 900 divided by 250. Those cancel, and now x will be the log base 1.025 of 900 divided by 250. Right, there's absolutely no reason to do anything until I get all the way to this point. Now I can break the calculator out. I will stop doing this in just a little bit and just kind of like assume that you know how to use this at this point. Whoops, that didn't work. Let's try that again, 1.025. I can even put my fraction bar in if I like that instead of my division. There it is, log base 1.025 of 900 divided by 250, and we have it, right? My x in this case, 51.875, etc. So it looks like it's going to be 51.88. Let's put that away in a second, 51.88. And again, what I want you to consider is how much faster this is than either the use of the method of common basis, which I still like as a method, or certainly much faster than graphing both sides of the equation, finding out where they intersect. Now, don't get me wrong. There's still plenty of instances where that method, the graphical method, not the method of common basis, but where the graphical method would actually be better and easier to use than this. But in each one of these cases, it's very, very easy and very, very quick to use a logarithm to solve these exponential equations. So let's keep working with them. Move my little pen icon over. Now, let's take a look at some applied problems. Many of our problems from the previous unit, required us to solve exponential equations graphically because we had no algebraic methods to do so. We can now use logarithms to make this process faster. And again, I still think that graphically sometimes it makes a lot of sense, you know, because maybe you want to see the population graph going up, and maybe you want to then see a horizontal line where the population hits some kind of a number, you know, some kind of a level. I like that. I think that that's got a lot of value to it. But if you're just looking for the answer to some kind of, you know, equation solving question, logarithms are your opportunity. Let's take a look at exercise number 4. A bank account earns 2.5% interest compounded once a year, all right, so not monthly or quarterly or anything like that. If $325 is invested in the account, determine algebraically how long it will take for the investment to be worth $700. round to the nearest year. All right, well, what I'd like you to do is I'd like you to pause the video, all right? See if you can set up the exponential model that models the amount that's in this account over time. That should be something you're comfortable with, not just from last unit, but even from Algebra 1, because this isn't quarterly compounding or monthly compounding, it's just compounding once a year. Then see if you can set up an equation, right, that you're trying to solve, and then try to solve it using logarithms. Pause the video now and see if you can get all the way through that. All right, let's do it. So first, let me just model the amount that this savings account is worth, right? So the amount that it's worth is going to always equal that principal amount, 325. It's growing, right, at 2.5%, so it's really 1 plus 0.025. The compounding is just once a year, so it's just to the t. Maybe make this model a little bit easier to work with. A of t equals 325 times 1.025 to the t. All right, so there's our model. Now, what equation are we trying to solve? Well, we're trying to solve the equation 325 times 1.025 to the t is equal to 700. All right, let's talk about this for a moment. If you're able to write this down right from the beginning without having to write this and then this down, that's completely okay. There's no problem with that at all. But now we're really doing a problem that's almost identical to letter C in the last exercise, right? So what we're going to do is we're going to divide both sides by 325. And perhaps 700 divided by 325 is a nice number. Perhaps it's not. I don't really care. I really don't. I don't want to know what it is. All right, because I'm going to leave it as 700 divided by 325. And then I'm going to take the log, base 1.025 of both sides of this equation. That was fun. Now I just want to send that thing bouncing around the screen. All right, I'm going to take the log base 1.025 of both, and now t is just going to be equal to that. The log base 1.025 to the 700 divided by 325. And if you do that on your calculator, what you end up seeing, and we're going to stop with breaking the calculator out for right now, it'll come back out one more time this lesson. But what we're going to do right now is we're just going to type that in. We're going to use 1.025 as the base. And what we're going to see is that is not what that's equal to. Wrong sheet. That's going to be 31.0722. It says round to the nearest year, so that's going to be 31 years. All right. Think about how much faster that is than having to graph, this thing, and then y equals 700, finding a good window, et cetera, et cetera. Much, much faster to do it that way. All right, so great little review of a growing exponential using interest. Let's take a look at maybe one that is actually decaying, exercise number 5. Radium-219, or 219, has a half-life of 10 seconds, very fast. How long would it take a 50-gram radioactive sample to have only 2 radioactive grams remaining? Round to the nearest tenth of a second. So again, what I would suggest doing is first modeling the amount of the radium-219 that is still radioactive based on our half-life lesson from the last unit. Then set up an equation that you're trying to solve, and then work through it using logarithms. Pause the video now and see what you can do. Now again, keep in mind, what it means to have a half-life of 10 seconds. It means after 10 seconds, that 50-gram radioactive sample has become a 25-gram radioactive sample. After another 10 seconds, so a total of 20, that 25 has gone to 12.5. Another 10 seconds, that 12.5 has gone to 6.25, etc. After that, I don't know, because what's a quarter divided by 2? Who knows? Maybe it doesn't even exist. So let's now take a look at the model. I was kidding, it does exist. So the amount that's radioactive at this point, right, is going to be what we start with, which is 50, times 1/2 to the t divided by 10. Remember, we've got to have that exponent of t divided by 10 to take into account that the half-life, or the number of half-lives, right? That's actually the exponent. The number of half-lives is the amount of time that has passed in seconds divided by 10 seconds per half-life. Now what we want to do is set up and solve an equation. And the equation that we're trying to solve is 50 times 1/2 to the t divided by 10 is equal to 2. Okay, so what are we going to do? Well, we're going to divide both sides by 50. And again, I could reduce 2/50ths to 1/25. I could then make that 0.04. You know, there's a lot of things I could do, but I don't need to. I can just leave it like that. I have 1/2 to the t over 10 is equal to 2/50ths. Now I can take the logarithm base 1/2 of 1/2 to the t over 10 is equal to the log base 1/2 of 2/50ths. Whoops, not 2/20ths, but 2/50ths. Let me extend the page, give myself a little bit more room. Those are going to cancel. That's going to leave me with t divided by 10 is equal to the log base 1/2 of 2/50ths. And now I can multiply both sides by 10. And t ultimately is going to be 10 times the log of 1/2 of 2/50ths. And that might be a little bit complicated to put into your calculator, but I would, wow, just a curve everywhere. But I would much rather put that into my calculator than have to be carrying decimals along the way. I don't want to have to do that. So ultimately, though, when I plug all of this into my calculator, my t value ends up being 46.43, etc. This asked me to the nearest tenth of a second, so that's going to be 46.4 seconds. All right. Again, so fast with logarithms, and it makes sense, right? Logarithms are just a natural extension of how we use inverse operations to solve any equation. You know, how we use square roots to solve equations with squaring, right? Or how we use division to solve equations that have multiplication in them, right? Logarithms allow us to solve equations that have exponentiation in them, where the exponent is the variable. All right, let's keep going. Finding inverse functions. We can use this relationship, right, the inverse relationship between exponentials and logarithms, to find equations of inverses of more complex exponential functions. So we should feel comfortable now with the idea that, oh, if we've got the exponential function y equals 2 to the x, its inverse is y equals log base 2 to the x. But what if the exponential function is a bit more complicated, more complex? Let's take a look at exercise number 6. Find the equation of the inverse of the function y equals 2 to the x minus 7 plus 5. Awesome. Well, step one, whenever we want to find the equation of an inverse, is we take our original function and we simply swap the roles of x and y. So step one, literally, is to say x is equal to the y minus 7 plus 5. That is step number one, anytime we're solving for an inverse function equation. Now what I'd like you to do is pause the video and see if you can use inverse operations to solve this for the variable y. So I want y equals at the end of all of this. Pause the video now and see what you get. Awesome. Well, keep in mind, if I'm solving this for y, let's just go through it, right? Y has had 7 subtracted from it, then the exponentiation occurred, then the addition occurred. So I need to get rid of that by first doing the subtraction, then doing the logarithm, and then doing the addition. All right? I mean, I can just see it, right? I'll subtract 5 from both sides, and that will give me x minus 5 is equal to 2 to the y minus 7. Now I'll do the log base 2 of both sides in order to get rid of the exponentiation. That'll cancel. That'll give me the log base 2 of x minus 5 is equal to y minus 7. And now I can add 7 to both sides. Remember, you can't add within that logarithm argument. That x minus 5 is trapped there. So we'll just have y equals log base 2 of x minus 5 plus 7. And let me make that look just a little bit more like an x. And you can really see it, right? You can see every single inverse operation from this one down here, and in the opposite order, right? The last thing we do in this function is add 5. The first thing we do in this function is subtract 5. The second thing here is the exponentiation. The second thing here is the logarithm. The last thing up here, right, the first thing up here is subtracting 7, and the last thing down here is adding 7. Every operation that's up here has its inverse operation down here, but in the opposite order. Now, there's one more thing that we want to kind of take a look at, and it's almost a historical artifact at this point. Solving using any base. You can solve any simple exponential equation using actually any logarithm by using the power law for logarithms. And we looked at obviously the 3 major logarithm laws in the last few lessons. But let's see how we can use that last logarithm law to solve actually any exponential equation using any base, which is a little weird because you naturally just want to use the base that is most appropriate. But strangely enough, it used to be that we only used either a base of 10 or a base that we're going to introduce in the next lesson in order to solve logarithms. So let's take a look at exercise number 7 and see how that's done. Consider the equation 7 to the x equals 20. Solve this equation to the nearest hundredth by, letter A, using a log with a base of 7. Now that is the natural way to go, all right? There's no way I want to solve this thing using any base but 7 until we hit letter B, and then we're going to use a different base. But what I'd like you to do is pause the video really quickly and figure out what the value of the solution to this thing is to the nearest hundredth by using a base of 7. All right, let's go through it really quick. Simple, right? I mean, like literally, this is like, we should have included this in 6th grade when we were doing one-step equations, because this is literally a one-step equation. We're just going to take the log base 7 of both sides. That's going to cancel. X is equal to the log base 7 of 20. All right, we can just plug that into the calculator. I won't waste your time right at this moment doing that, but it's like 1.539, etc. So to the nearest hundredth, that's x equals 1.54. And that is definitely the way that I'd like to see you do it, okay? But, little history lesson, math history. Again, it used to be that the only real logarithms that were on any kind of a calculator were the log base 10, known as the common log, right? That's when we write the log without the 10 down below, all right? Or something called the log base e, and we'll get into that in the next lesson, so no worries about that. So it used to be, anytime you solved a logarithmic equation, you pretty much always used the log base 10. So let's see how we can now use the log base 10, letter B. Solve this equation by using the log base 10. All right, let's go through it together. Now, one thing that this relies on is the following logarithm property, right? We had this logarithm property that said the log base b of, let's say, x to the, well, let me do a to the x is equal to x times the log base b of a, right? So in other words, we had this logarithm law that said if you took the logarithm of something raised to an exponent, that exponent could come out, all right? Great, awesome. So how is that going to work here? Well, let's take a look. All right, I have 7 to the x is equal to 20. And now I'm just going to do the log base 10, but I'm just going to maybe I'll put the base there anyway because my calculator is going to force me to put it in. So I'm going to do the log base 10 of both sides. All right, now unlike before, I can't just cancel the log and the exponential because they don't have the same base. But what I can do is bring that exponent out, and I'll have x times the log base 10 of 7 is equal to the log base 10 of 20. Now, the log base 10 of 7 is an ugly number, as is the log base 10 of 20. And I don't want to know what either one of those numbers are. They're a number. I have a number multiplying x is equal to another number. To get x all by itself, I'm just going to divide both sides of this equation by the number multiplying x. So I'm now going to divide this side of the equation by log base 10 of 7. And here I'm going to pull the calculator out one more time. That'll cancel. So x now is the log base 10 of 20 divided by the log base 10 of 7. Okay, so on some of your calculators, that log base 10, well, actually, let me go with the fraction bar just to make our lives a little bit simpler. So I'm going to do the log base 10. Oh, come on now. The log base 10 of 20. I got to get rid of that 0 eventually. Otherwise, I'm going to get an answer of 0. The log base 10 of 7. Let me get all the way out and delete that. And now hit enter. And there is our 1.54 again. Keep in mind, right, what we had before. 1.54, we're getting that again right here. Now, you can see the obvious disadvantage of this, right? I've got two logarithms now floating around, the log base 10 of 20 and the log base 10 of 7. It's very unnatural, right? Why would I take the log base 10 of 7 to the x instead of the log base 7 of 7 to the x? I mean, the log base 7 of 7 to the x answers the question directly, right? What do I have to raise 7 to in order to get 20, right? That automatically answers the question as opposed to going through this. But you never know. There are some math teachers that actually insist on this, even though this kind of function has been around on graphing calculators probably since the mid to early 1990s, all right? And I even used to insist on this because I loved using the power law of logarithms in order to solve exponential equations. But now that our graphing calculators can evaluate a log with any base, there's very little reason to do this other than the idea that you might somehow get tested on it in some way, shape, or form. All right. It is, again, still kind of a historical artifact. So I just want you to keep that in mind as we do the final exercise in this lesson. Exercise number 8. Solve each of the following using the common log, base of 10. Round to the nearest hundredth. All right. Now again, normally, you know, if you've got a calculator, it's got logarithms of any base. I'm going to do this one with a base of 5, this one with a base of 0.25, and this one with a base of 1.05. But in this particular problem, it says solve each of the following using the common log, the base 10. So I'd like you to try to do that using the logarithm law that we did up above. Actually, how about this? Try to do that on letter A. Then we'll go through letter B together, and then I'll have you do letter C on your own. So pause the video right now. See if you can solve letter A using the common log instead of a log base 5. All right, let's do it. And again, there's nothing really all that special about the common log either, except for the fact that historically it was one of two that was actually on your calculator. So I'm going to take the log base 10 of 5 to the x is equal to the log base 10 of 30. And again, I don't care what the log base 10 of 30 is. That logarithm law is going to allow the x to come out. That's going to be x times the log base 10 of 5 is equal to the log base 10 of 30. All right, now I can divide both sides by log base 10 of 5. Very, very similar, obviously, to the problem that we just did. I find now that x is equal to the log base 10 of 30 divided by the log base 10 of 5. We just need to plug both of those into our calculator. And what we find, it's very messy, as many of these are, 2.113, etc. To the nearest hundredth, that's 2.11. All right, so hopefully, based on what we did in the previous exercise, that one was pretty easy for you. Now, why don't we go through this one together? Now, again, I want us to think about this for a second, right? You know, again, it would be more natural to take and do this with a log base 0.25, you know, a log base 1/4, okay? But we're going to, again, do it log base 10. Now, it doesn't really matter in terms of order of operations, right? You know, we've got the 0.25 exponentiated is equal to 0.8. That subtraction of 10 from the exponent is the first thing that was done. So it's actually going to be the last thing that we will undo. So the first thing I'm going to do in this situation is I'm going to do the log base 10 of 0.25 to the x minus 10 is equal to the log base 10. Now, of course, I have not enough room, of 0.8. That's going to allow me to pop this out. Now, that's a little bit dangerous. I'm going to put it in parentheses since it's a binomial. So that's x minus 10 times the log base 10 of 0.25 is equal to the log base 10 of 0.8. Boy, letter C is really going to be unhappy with me. I'm now going to divide both sides by the log base 10 of 0.25. You guys are going to be like, there's a line going through everything, Kirk, and there is. So divide both sides by log base 10 of 0.25. Cancels that out. I don't want to know what that ratio is equal to. I'm just going to now add 10 to both sides. So ultimately, x is equal to the log base 10 of 0.8 divided by the log base 10 of 0.25 plus 10. Right? So that is the exact answer, for what x is equal to. Now, doing log base 0.25 would have certainly made this easier. We wouldn't have had this fraction, right? We would have just simply had log base 0.25 of 0.8 plus 10. That would be our final answer. But when we substitute this into the calculator, if we're careful about it, and we crank through all of our work, we will end up getting 10.16 as our final answer. All right. So now what I'd like you to do as a final exercise, hopefully you have enough room, because I don't, I'd like you to try to do that equation, and maybe we'll rewrite it down at the bottom so we have more room. Go ahead and pause the video and see if you can figure out what the value of t is to the nearest hundredth in letter C. All right, I'm not gonna even try to squeeze it in here. I'm gonna just rewrite the problem down below so that we have plenty of room to work on it, hopefully. Let's just extend the page. And letter C, what we had was 15 times 1.05 to the t is equal to 40. Now, the first thing I want to do before I take the logarithm of both sides is I want to isolate the exponential, right? Don't forget about your order of operations. That multiplication by 15 comes last, so it's the first thing I'm going to undo. Now I'm going to take the log base 10 of 1.05 to the t is equal to the log base 10 of 40/15ths, whatever that is, I don't care, right? That's going to pop that out. All right, that means I'm going to have t equals, t times the log base 10 of 1.05 is equal to the log base 10 of 40/15ths. Now we're going to have some fractions within fractions, but that's okay. Can have a complex fraction here and there. We're going to divide this by the log base 10 of 1.05. Those cancel. And yeah, this expression is not the prettiest thing on earth, and it would be a lot easier if we were doing the log base 1.05, because that would be just the answer. It would be this thing, but with a base of 1.05. So you're probably thinking, why are we doing this? Historical artifact, I get it, whatever. But when we crank it into our calculator, our final answer, rounded to the nearest hundredth, will be 20.13. All right, and that's it, right? So if you just have to solve an exponential equation, and they don't say use this or that, and quite frankly, they probably won't, right? In all likelihood, in sort of a free response scenario, you can use base 10, base 1.05, hopefully in this particular problem, anything you want. But I could very easily see a multiple choice question coming up where they give you something like this and they say, which of the following is the correct answer? And all the answers are phrased in terms of the log base 10, in which case they might not even write the 10, right? Because with the common log, often that 10 is not even written. And again, that's because the log base 10 was the first logarithm out there, and so they didn't even conceive of, oh, let's put a little number down there for the base. It was just like, oh, the logarithm gives us its output, what you have to raise 10 to get the input. but now we can do a logarithm of any base. All right, so let's wrap this up. The whole purpose of today's lesson was to really extend your ability to solve equations by using inverse operations. The key is, when we're solving an exponential equation where the variable is in the exponent, then to reverse that process, we have to do a logarithm of the same base as whatever our exponential was. So if we have 2 to the x equals 5, to get rid of the 2 to the x, we take the log base 2 of both sides. And it really doesn't matter what that base is because our calculators can handle any positive base out there. Again, for historical purposes, what we looked at right at the end is that based on the third exponent law, you can really use any base that you want to solve an exponential equation. But that being said, there are more wise choices than others. All right, so if you can use whatever the natural base is for the equation, go ahead and use it. All right, well, we're going to work more with this as we introduce a brand new number to you in the next lesson. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.